Application of Gauss's theorem. First application of Gauss's law, we are going to calculate the field due to an infinitely long straight uniformly charged wire. Let us consider an infinitely long thin straight wire with uniform linear charge density lambda. That means we consider an infinitely long straight wire. This is the wire which is infinitely straight. That means it extends to infinity, right? And this has lambda linear charge density. That means this wire is uniformly charged and the charge density, that is line charge density, is lambda. Lambda is the line charge density, and again we consider this as plus lambda, right? Now the wire is symmetrical about its axis. Is symmetrical about its axis. Since this is infinitely extended, then you can say that field at any point near the wire will only depend on the distance from the wire, and it will be directed away from the wire. See here, if this is the wire which is charged with plus charge, right? Now say this is the point, then what is the field intensity? Since this is infinite, then you can say field lines are radially outward. That means we can assume the field lines are starting from the wire. It will be directed away from the wire in each and every point. If this wire finite, then at this point field line will be along this also. That means if the wire is finite, then we cannot say that each and every point electric field lines are radially outward, and it only depends on the distance from the wire. But since we have assumed the wire as infinite, then we can say that this is the symmetry, right? Then we can say at each and every point the field lines are away from the wire, and electric field only depends on the distance r from the wire. Let us see. We have to find out field at point P which is at a distance r from the wire. To calculate the field at P, let us consider a closed Gaussian surface, and we take this Gaussian surface as cylindrical surface whose axis is the wire, and radius of the cylinder is r, and height of the cylinder is a. Let us consider a cylindrical Gaussian surface of radius r and length L around the charged wire. The direction of the electric field at every point must be radial and also equal in magnitude at every point on the curved surface of the cylinder. Now, Gauss's total flux through this closed surface S is equal to E dot ds will be equal to Q enclosed by epsilon 0. Q enclosed is the charge inside this surface. Now we can divide this closed surface into three surfaces. One is the top surface. This is top plane surface S1. Other is bottom plane surface. Let us say this is S2. and other is curved surface. That means if this is the cylinder, then this top is the plane surface. This is S1, the bottom. This is also plane surface. This is S2, and this, the curved surface of the cylinder, this is S3. Then we can say E dot ds through S1 plus E dot ds through S2 plus E dot ds through S3 will be equal to Q enclosed, that means charge enclosed in the surface is, since length of the wire is L and charge per unit length is lambda, therefore total charge enclosed in this surface is lambda into L divided by epsilon naught. Now see here, we have already told that field at this point, that means field at the top surface will be along radial, and the surface area, the direction of the surface area will be along upward direction. That means in this surface on the top of the cylinder, E is perpendicular to ds. In this surface, E is always perpendicular to ds. Similarly, at this surface, E is along this direction is radial, but direction of the surface is perpendicularly downward. That means here also, at each and every point, E is perpendicular to ds. Here also, E is perpendicular to ds, but in this surface, this curved surface, for this curved surface, the direction of the surface area will be radial, as well as direction of the E electric field will also radial. Therefore, for this surface, E is parallel to ds vector. So you can write, this is 0, E dot ds, E ds cos 90, which is 0, through this surface also 0, and through this surface is E ds cos 0, E ds cos 0, which is lambda by epsilon. Or we may say 0, need not write to 0. Now, since the radiuses are, therefore at each and every point on the curved surface distances are, and we have said that due to the symmetry of the problem, E is only depend on the R. Since R is constant, therefore E is constant. So bring it outside the integration. Therefore you can write over ds is equal to lambda L by epsilon. Now integration ds means the total surface area of the curved surface. Total surface area of the curved surface, which you can write E into 2 pi RL. Curved surface area of the curved surface is 2 pi RL. How will you get it? This is the surface. Now, say this is the cylinder, right? Say this is the cylinder. This radius R, this is length L. Now, surface area of this surface, right? Surface area of this curved surface. What will be the area? If we cut here, then it will be a rectangular surface whose this is the length, which is 2 pi r circumference of the circle, and this L. Therefore, you can say E into 2 pi r L is equal to lambda L by epsilon 0, or E is equal to lambda by 2 pi epsilon naught r. L cancels out. Lambda divided by 2 pi epsilon naught r. And in vector form, you can write E is equal to lambda r hat divided by 2 pi epsilon naught r, because the field is radially outward for plus charge. If the wire is charged with negative charge, then it will be along minus Rn. That means it will be towards the surface or toward the